Hello, welcome to Dr. White's Fun with Graphs. On this one, I'm going to imitate a famous painter, and we're going to draw a bunch of happy trees. So first, a graph is connected if for any two vertices in the graph, there is a path containing those two vertices. This path is a subgraph of G, of course. So for instance, this graph on the left is not connected because there is no path from U to V. Because remember, these edges, even though I've drawn them so they look like they have an intersection point, that intersection point is not an actual vertex of the graph. This is actually 4 cycles drawn in a funny way. So it's a disconnected graph, which is disconnected is what we say when something is not connected. On the other hand, if I just add an edge between those two vertices, now the resulting graph you can see is connected. How do we know that? Well, any two vertices on the diamond on the left are connected by a path because you can see that a 4 cycle is definitely connected. Any two vertices on the right are connected by a path because you can see that this graph is also connected. And if you have a vertex on the left and a vertex on the right, there's a path between them because you can go, say, if I pick X here and Y here, I could first go to V, go across that edge I created, and then go down to Y. So this is a connected graph. Now, in lots of applications you want connected graphs. For instance, if you're talking about a computer network, you definitely want it to be connected. And we all know what happens when the Wi-Fi disconnects. It's not very pretty. Likewise, highway networks usually are connected because you kind of want to be able to drive from any house to any other house. Another definition in graph theory is called being acyclic. A graph is acyclic if it does not have any cyclic subgraph. There is a perspective, a linear vector space in the background I won't discuss, but from that perspective, the notion of connected is related to being a spanning subset, and the notion of acyclic is related to being linearly independent. Somehow the point is that a cycle has more edges than the minimum amount you need, because on a cycle there's 2 ways to get from point A to point B. So in an acyclic graph you don't have any of these types of redundancies where there's more than one choice, which allows us to arrive at our definition of a tree. A tree is a connected acyclic graph. So between any two vertices in the graph, there's a way to get from point A to point B, and there are no cycles. And it's called a tree because when you draw it, it looks vaguely like a tree. And so you can see, because as you can tell, there's no cycles on a tree. Trees start from a root, you go up the trunk, they branch out. Any 2 points on a tree, it's possible to connect from one to the other. So it is connected and acyclic. Now, one of the theorems the book proves is that a graph is a tree if and only if every pair of vertices is connected by a unique path. So here what we mean by unique is a unique path whose endpoints are those 2 vertices. So this is a statement of the form P if and only if Q. We're going to essentially do the proof from the book, but I'm going to actually state it in its equivalent form, and instead of talking about contradiction, we're actually just going to prove not P if and only if not Q. In other words, G is not a tree if and only if there exists a pair of vertices that is not connected by a unique path, which means either it's not connected at all or it has more than one path. So first, let's assume G is not a tree. That means either that G is not connected or that it has a cycle. Suppose G is not connected. What does that mean? That means there exists two vertices, U and V, such that there is no path from U to V in G. But that means there exists a pair of vertices that is not connected by a path. So certainly can't be connected by a unique one. We managed to prove not Q. Okay, suppose G is connected. Suppose G has a cycle. Let C be a cycle in G. Take two vertices on the cycle, U and V. If you go one way around the cycle, you get one path. If you go the other way around the cycle, you get a second path. So we see that in G, U and V are connected by at least two paths. So they're not connected by a unique path. So we've managed to show not P, G is not a tree, then not Q. There exists a pair of vertices that are not connected by a unique path. So that's exactly what this is stating. Now we're going to assume not Q. Now assume there exist pairs not connected by unique paths, and we're going to show G is not a tree. Case 1, you found a pair of vertices that are not connected by any path. Well, then G is not connected. Case 2 is actually a lot harder. Suppose U and V are connected by two paths. In general, you don't have much control. So you know you have one path, and you know you have a second path. The second path could overlap and intersect the first path numerous times. So we can't just take the union of the two paths and say we have a cycle. We got to be a little bit more clever. How are we going to be clever? Well, if you list the vertices in order on both paths, we know there's going to be some segment at the end where both paths overlap completely, where both the vertices on both paths are always the same. So we're going to let W be that vertex. Once you've made that choice, there must be some other last intersection point, common intersection point before W. Now, of course, there is a point to be made. You have to prove W exists. We know W must exist because at the very least both paths intersect in V. So we know at the very least, in the worst case scenario, W is equal to V itself. Likewise, we know X exists because in the worst case, X is equal to U itself. So we know these two vertices exist and are distinct. So what do we have? We have these two vertices. We know P1 and P2 agree on this part of the path after the cycle. And we know this is a common intersection point that they have in common, and that from X to W, they have no common intersection points anymore. In other words, that these vertices up here are distinctly different from these vertices down here. Well, then take a union of these two parts of the paths, and you see what I drew is a cycle. So by being slightly more careful, we see that you do in fact get a cycle. So G is not acyclic and therefore not a tree. If you have at least two paths, you must have a cycle somewhere in the graph. Note that this proof does not tell you that the cycle has the vertices U or V necessarily. So what this theorem shows us is exactly something you could see from drawing a picture of a tree. Given any two vertices in the tree, there is one and only one path connecting them. It's somehow the minimally connected graph you could have. It's connected, and if you delete any vertex remaining in the graph or any edge remaining in the graph, it is no longer connected. Not vertex, edge. If you delete any of the remaining edges, you're going to disconnect the graph. We also notice once you have a tree, you've got these funny features. There's these vertices of degree 1 that always seem to exist. A vertex of degree 1 is called a leaf. So here's a fact. Trees have leaves. Proof 1. Just go outside to the nearest tree in your neighborhood and look for yourself. Of course, kidding aside, let's prove that this definition of a leaf is true. So we're going to try to show that every tree has to have a leaf. It turns out the shortest proof I know of is the following one. You let P be a longest path in the graph G. So take the longest path that exists and let the two extreme endpoints be x and y. Now suppose that x and y have degree bigger than 1. Well, that means x must be adjacent to more than one vertex. If it were adjacent to a vertex that was not on P, then you could have made the path longer by adding w to the path. But you picked the longest path possible, so that's not possible. No such w exists. So if the degree of x is bigger than 1, and the x must lie on another edge, where does the other endpoint of the edge have to be? It has to be on the path. Congratulations, you have found a cycle. So we found a cycle in a tree. And if you find a bicycle in a tree, you probably should call the fire department or go get a ladder. In a math class, what you have found is actually a contradiction. There are no cycles in trees. So the conclusion must be that the degree of x is actually 1, so x is a leaf. Notice here that the exact same argument actually applies to y as well. If the degree of y were bigger than 1, then y has to be adjacent to another vertex. If we're adjacent to a vertex that was off the path, then you would be able to construct a longer path, which contradicts the definition of longest. So it would have to have a neighbor or an edge to an endpoint on the path, and then you would have constructed a cycle, which is a contradiction. So the degree of y is also 1. So overall, we see that we get a cycle exists, which is a contradiction. So in fact, x and y are leaves. So not only do trees have leaves, but you can always guarantee that in math, trees have at least 2 leaves. In other words, there's never winter for trees in graph theory. The leaves do never completely fall off the tree. There's always 2 remaining. With this little caveat, you need to have at least 2 vertices. If you check very carefully, I was actually assuming x and y are distinct. If you take the tree with 1 vertex, this argument doesn't work very well, and that tree only has 1 leaf. So if you have at least 2 vertices, you have at least 2 leaves. That is as best as possible because the path graph always exists. And the path graph is a tree, is connected, and it has no cycle. And it has exactly 2 leaves. So now we're going to prove another interesting claim about trees. The number of edges in a tree is always the number of vertices minus 1. This proof uses induction on the number of vertices. So you're going to have to skip this argument if you haven't taken a proof writing course. Although it's kind of useful because it shows how induction is usually done in graph theory, and it's not the same way as it is normally done in a proof writing course. Because in a proof writing course, you assume the statement is true for some value integer, non-negative integer n, and you prove it's true for n plus 1. Here you will see that we actually try to make a smaller graph instead, and then apply the induction hypothesis. And that's usually what is done in graph theory. So, induction on the number of vertices. First, suppose you have one vertex. A one vertex tree is not very interesting. It has 0 edges, and 0 is clearly 1 minus 1. All right, suppose you have at least 2 vertices. Then G certainly has a leaf. What we're going to claim is that when you delete a leaf, the result is still a tree. If that's true, then you can apply the induction hypothesis to give you that the number of edges in G minus L is the number of vertices minus 1. How does that help you? Well, I mean, let's just draw the picture to get the idea. When you delete the leaf and delete the vertex, when you delete a leaf, you're deleting exactly one vertex and one edge. So the number of edges of G is the number of edges of this deleted graph plus 1, and the number of vertices is the number of vertices of the deleted graph plus 1. So you're adding 1 to both sides, so the equality is still true. So all I need to show is that G minus L is a tree. All right, so first let's show that it's connected. Take 2 vertices in G minus L, like here and here. Well, because there are also vertices in G, and G is connected, since it is a tree, there must have been a path from U to V in G. Your only concern is, what if that path used the leaf? Well, let's think about that. Suppose your path used the leaf. Well, vertices on paths have to be distinct. And since L is not in this deleted graph, L has to be midpoint on the path. And so then we see that the degree of L is at least 2, which contradicts the definition of leaf. So the result is that L couldn't have been on the path, which means that the path is actually in the deleted subgraph. Therefore, between any 2 vertices in G minus L, there is in fact a path in G minus L between them. So G minus L is connected. All right, so why is G minus L acyclic? Well, if you take any subgraph of G minus L, then it's actually subgraph of G. Since G is already acyclic, we see that H can't be a cycle. So again, G minus L is acyclic. Acyclic connected graphs are trees. Therefore, the picture you see is in fact true and isn't just a result of the example we picked. If you take any tree and delete a leaf, you get another tree. So the reason why we do induction the way we do it in graph theory is because normally in lower level courses, they say go from P of n to P of n plus 1. In graph theory land, that would say start with a graph on n vertices, and then try to create a larger graph. But the issue you have there is when you add your new vertex, you wouldn't actually get any control over who his neighbors are or what edges are incident to that vertex, and that creates a problem. Instead, what we often do is we start with a graph, we make a clever choice of V so that we know exactly which edges were incident to it, and then we cut it out and remove it. And now you have a smaller graph. And then you apply induction to the smaller graph, and then you use your knowledge about what you removed in order to manage to finish your argument. And that's what we did here. In fact, you had to be careful which vertex you removed, because if you remove an arbitrary vertex from a tree, the result isn't always a tree. So Being able to do things this way gives us more control. We get to control which vertex we delete so that we can actually apply induction. In this other approach, if I started with this tree and I decide to add a vertex, well, how am I going to add it? There's no rule that says that I have to add the vertex with neighbors in such a way to ensure that it's a tree and has no cycles. And even if I say, well, add edges so that there's no cycles, well, where am I going to add the edges? There's too much room for interpretation. It's not clear what I'm going to do. So it's much, much smarter to do the other direction.